How does Gibbs free energy describe chemical energy? Imagine a chemical reaction as a race between energy and disorder. Gibbs free energy helps us understand which reactions can happen naturally and how much energy is available to do work. It's like an energy balance sheet for chemical systems. Gibbs free energy is a number that tells us the maximum useful work that can come from a chemical process when temperature and pressure stay the same. It connects the energy stored in chemical bonds, called chemical energy, to the ability of a system to cause change or do work. At its core, Gibbs free energy is calculated by taking the total heat content of a system, known as enthalpy, and subtracting the product of temperature and disorder, called entropy. The equation looks like this. Gibbs free energy equals enthalpy minus temperature times entropy. This means that the available chemical energy depends not only on how much energy is stored in bonds but also on how disorganized or spread out that energy is. When energy is more disordered, less of it is available to do work. When a chemical reaction occurs, the change in Gibbs free energy, called delta G, tells us if the reaction can happen on its own. If delta G is negative, the reaction releases energy and can happen without extra help. This is called a spontaneous reaction. If delta G is positive, the reaction needs energy input to proceed. And if delta G is 0, the system is at a perfect balance or equilibrium, and no net change happens. In real life, Gibbs free energy helps explain how chemical energy powers everything from engines to living cells. For example, in our bodies, reactions with negative delta G provide energy for muscle movement and other vital processes. In engines, chemical energy from fuel transforms into heat and motion, guided by the principles of Gibbs free energy. So, Gibbs free energy acts like a bridge between the tiny chemical bonds inside molecules and the larger energy changes we see in the world. It shows us how much chemical energy is available after accounting for energy lost to disorder. This way, we can predict whether a reaction will happen naturally and how much useful work it can produce. Understanding this helps us see how energy flows and transforms in all kinds of systems, from biological to mechanical.